Hello everyone. So in this problem we'll discuss the question of CTQ 6. So what was the question? Actually we have to plot the transfer function on log scale. So before finding the exactly the transfer function, what should we know? Actually what is the transfer function and what are the parameters that are included in the transfer function? In that your DC gain, 3 dB frequency, or I can say poles, zeros, a location of pole and zeros. From that we can simply write a transfer function in general. But exactly before going into the transfer function, we will see this circuit, because this is the circuit was asked last year in interview. I will not mention the name of the company, but yeah, it was asked in some company. So the question is, we have to look at the structure and find the transfer function. So the general criteria for any in general transfer function is that we have to find the pole and the zeros and then put into the equation. So first I will like what the transfer function is. Okay. In general, the transfer function that we call V out by V in, we should have the knowledge of DC gain. After that, 1 minus S G1, 1 minus S Z2, so on. Means there are zeros at Z1, Z2, 1 minus S by P1. So I am writing here minus, it means these Z1, Z2, P1, P2 are negative quantities or the frequency on left hand side. That's why I am writing like this, Sy P2 and so on. So this is general transfer function. So for the first order system, what do you like for first order? What I will write, V out by V in. If there is no zero in terms of S, what do you write? A naught divided by 1 plus S by omega P1. So mean to say the omega P1 is nothing but a left side frequency. The pole 1 is at minus omega P1, directly indicating that left half plane pole, that I can say. Okay, so this is the general expression for the first order system. Now we will see how this circuit is behaving, what should be our analysis, and so we'll conclude the transfer function later on. So any differential circuits we can see here, it is simple circuit which is a resistive load is there. Yeah, this is my input 1, input 2, and in between the output there is a capacitor that I call V out 1, V out 2. So we can analyze usually for the differential circuit analysis. What we do, we can analyze like a half circuit analysis. We can do half circuit analysis for fully differential circuits. So this is a fully differential circuit because there are two outputs and two inputs, differential inputs, differential outputs, and the circuit is symmetric. So what is the initially we can do for this small signal analysis? This RD circuit can be simply written as 2C in series, and midpoint can be virtual short. We will see this thing. So for SC analysis, this point is virtual short. Why it is virtual short, I think every one of you knows. But this input I will write differential analysis. This is a plus VID by 2 and this is minus VID by 2. Okay, so the difference is nothing but VID only. So differential inputs, what is V in 1 minus V in 2 is nothing but VID. It is called differential input. Okay, it is my differential input, VID. Okay, so what you'll see, we can see the circuit is symmetric around its midpoint. So we can do the half circuit analysis. So it is like a symmetric. So what we can do, I am considering this is an ideal current source. If it is not ideal, then its R naught will be considered. Let's say it is okay. So R naught will be considered for non-ideal. For non-ideal current source. Okay. So these are the basics everyone knows. So this circuit can be means divided from the mid, because the C can be written as the 2C and it can be this midpoint can also be virtual short. So what can be written as, so the thing that we can conclude here, this point is also virtual short, this point is also virtual short. So I can write the half circuit in two ways. How I can write the half circuit? So the half circuit can be like, this is my virtual short, this is RD, and okay, parallel to RD, yes, parallel to RD, one cap is there, which is 2C, it is also to ground. Okay, so this is my one of the outputs, and this is a common source amplifier with input 1 that I call VID by 2. This is my output 1. So what can be written in general? There are two ways to find a transfer function. Directly I can write this. What is the DC gain? DC gain we knows V out 1 y V in 1 is called the DC gain. Okay. So for that my capacitor will be open. So what you can write directly, minus GM RD. I am not considering this RDS as of now. Here the lambda is 0, so RDS is infinite. I'll consider later. So what you can see here, the minus GMRD is by DC gain. Okay. So now if I find the pole, then what is the pole frequency? So this is my half circuit, RD 2C. If we want to find a pole, for DC gain the capacitor was open. Now to find the pole, what we can do, this is my output, we can do one thing, we can find the capacitor at this node which is looking to the ground. So capacitor's output node is what? Cap at output node. Cap at output node is what? 2C. Impedance looking at output node is what? RD. Okay, I'm considering that RDS is infinite or very large, or RDS is too large or larger than the RD. So what you can say, pole frequency that I call omega P1, it is what? 1 upon 2C into RD, that I can write 1 upon 2RDC, whatever can be written. Okay. So I have DC gain, I have pole frequency. Now no other pole and 0 can be found here. For finding the output impedance, I will short the input. So there is no other pole and 0 in the system. It is a first order system. First order system. So what can be seen? V out 1 by V in 1 equal to, I can write V out 1 by VID by 2. It is equal to minus GMRD, which is my DC gain, divided by 1 plus S 2RDC. Okay, so this is the transfer function single sided. So what we can find for V out 2 by minus VID by 2, it is what? It is a minus GMRD by 1 plus S2RDC. Same thing. So I can find from the one side only, but I am writing just to represent. So what is my V out? 1, it is nothing but minus GMRD times this 1 plus S 2RDC times V in Y, or sorry, VID by 2. Similarly, we can find a V out 2, which is plus GMRD by 1 plus S 2RDC VID by 2. Okay, so from here we can find is coming out minus GMRD 1 plus S 2RDC 2 VID2 plus VID2. So it results into minus GMRD 1 plus S 2RDC VID. So overall transfer function can be written as this is, I can write as the output differential. So V out differential divided by V in differential equal to minus GMRD divided by 1 plus S 2RDC. Okay, this is the complete transfer function. Complete transfer function. What is this 3 dB frequency? 3 dB frequency is simply the pole frequency, which I will call omega p1 is 1 upon 2RDC. Okay, this is my 3 dB frequency. So DC gain I know. DC gain magnitude is GMRD. Okay, and for find the UGB when my gain is 1 or in dB scale 0 dB. So what can be written as this GMRD, if I take the magnitude, divided by root 1 plus omega 2 RDC omega square RD square equal to 1. So for the time being I can consider this bracket term omega RD into 2C square is much greater than 1. So we can directly write what is the UGB. GMRD, this expression can directly written as omega 2RDC equal to 1. So RD can be cancelled here. So what is my omega? This I call UGB. So I will talk little bit more about. Now this is the basic thing about this question. Now we'll go something more about it. So what is 3 dB frequency? What is 3 dB frequency? So if there is a first order function, transfer function, that is for an amplifier, A naught divided by 1 plus Sy omega P1. This is my first order transfer function. Okay. So how to understand what is the 3 dB frequency? We can do the analysis like this is the magnitude of the transfer function. I can write it as the magnitude of this. Okay. So what can we see? This the h of omega magnitude is equal to A naught for 1 is greater than omega by omega p1, or I can say when omega is less than omega by omega p1, so my magnitude is A naught. Okay, so this is the case 1. In the second case, what can we see? That when omega is greater than omega p1, greater than, or you can say much greater than, just the point is here, if the omega is greater than 1, then this 1 can be ignored. If this 1 is ignored, then what will remain? Only omega y omega p1 is remained, because omega is much greater than omega p simply means from this we can say it simply means omega y omega p1 is greater than 1. Okay, so what we are trying to see here, it is nothing but A naught omega p1 by omega. Okay, so I can also write it from the expression. It is called omega ugb, that is gain times 3 dB frequency. That is a later I will see it. Okay, so omega by omega ugb by omega, or we can simply write. Okay, so what we are seeing here, there are two cases. From one, omega by omega p1 is less than 1, then my magnitude is a naught. When omega by omega p1 is greater than 1, my magnitude of transfer function is a naught omega p1 by omega. So omega and denominator are showing there is a roll off. Omega and denominator is showing there is a roll off. So what we can see, on general scale, if there is a magnitude that I call dB, and there is frequency that I call on log scale, what we can see here, that for particular omega, that is a omega p1. So we have seen the frequency. There are two cases. This is my one case region, this is my second case region. Here omega is less than omega p1, or omega by omega p1 is less than 1, and here is omega greater than omega p1. So here what we are seeing, the my gain is constant. Okay, so gain is constant to a naught, and after that gain is rolling off. So as omega is increasing, gain is rolling off, because here the expression of gain is a naught omega p1 by omega. Okay, so here is a 20 dB per decade roll off. So what we can see here, this omega p1 is nothing but a frequency. Before that my gain is constant, after that gain is rolling off. So I can say this is my transition frequency. So from here what I can see, omega p1 is transition frequency. Before omega p1 gain is constant, and after omega p1 and after omega p1 gain is rolling off. So it means the gain is first time starting rolling off here. So somewhere here in ideal scale, or I will say on a practical scale, it is like that. So somewhere here this is my called 3 dB frequency. Okay, so from here we can see this omega, this is my 3 dB down. Okay, so omega p1 is nothing but a frequency of transition. So this is called a 3 dB frequency also. Also it is called 3 dB frequency, because my gain is rolling off first time. So gain is going nearly 3 dB down of its DC value, 3 dB frequency omega p1. Okay, so this is this much information about this plot. So we can see little plot about its phase plot also. We can see something more about its phase plot as well. So if I plot, this is my omega on log scale. So it is somewhere here. So what is this is called omega ugb, and this is called omega p1, which is a 3 dB frequency, and other plot is my, what we can see, as the first pole is coming at omega p1, so my angle is starting at 0, and it is reaching minus 45 here, and after that to minus 90. So this is somewhere here minus 45, and after much larger frequency, after omega p1 it is reaching minus 90. Okay, so the phase of the angle can be written as, phase angle of this system, I will say phase of h can be written as what, minus tan inverse omega by omega p1. So when omega by omega p1 is less than 1, or is much less than 1, this phase is nothing but it is nearly 0. So 0, or as we can see here, the system is so here if the phase starting at 0, okay, and when omega y omega p1 is greater than 1 or much greater than 1, my phase reaches to minus 90, and exactly at omega y omega p1 equal to 1, my phase is reaching at minus 45. That we can see from the expression. So this is a little information about the gain and phase plot of this particular question. Now we will see what more can we extract from this circuit. Okay. Okay. So now this is my circuit. Now I'm taking any random circuit and differentially we'll analyze that how the R naught can be inserted. How the R naught, because as of now I have considered no R naught, but we can conclude one thing here. R naught of transistor means RDS is infinite till point. But what we have analyzed, any if there are two current sources, my complete differential structure, fully differential structure. So what we can see about this circuit is same thing, 2 I naught. It is I naught, and there is a resistor that I will call R. So what we can write here, again it is a total symmetric circuit. So we can put a line of symmetry in between, and it can be result out that there is a virtual short in between. Okay. So here I can write R by 2, R by 2. Okay. So this is my midpoint. So we can virtually short it. We can short this node virtually because my circuit is symmetric. So this node is virtual short, this node is virtual short, and this node is virtual short. So what we can see from here now, okay, for this AC analysis, I'll open these current sources, no problem. Okay, so what we can see here, I am seeing one thing, that yeah, this is my 0, R by 2, 0, R by 2. Okay. So we can see one thing from here, as this node is shorted, so it can be shorted to this also, it is a virtual short. So how this circuit can be represented? This circuit can be represented like upside is totally open because there is a current source, or better I will mention the current source. Okay, I will mention the current source, not a problem. So from this node, this resistor R by 2 is shorted to this node because this node is already virtual short. I am not doing analysis here, so no need to open this current source. I am just telling the concept. This is I naught, this is I naught. Okay, so other current other resistor can be short like this. So what we are seeing here, because there is a R naught in between, this R can be split as a R by 2, and this R by 2 can be shorted at the mid. So because lower node is also shorted, we can short the R means R like this. R would be shorted to this virtual short node. So what we can see, it is nothing but representing the R naught of transistors. So this circuit is representing nothing but R naught of this transistor. So what I can say here, if now if switch to practical circuit, switch to lambda not equal to 0 case, means R out is not equal to infinite. Okay, so this thing can be concluded from here. Any particular R connected between two structures, differential structures, it is behaving like nothing but their R naught when we virtually short it. So what we can see here, the complete structure can be written as like this. So here we are smoothly inserting this virtual short effect, this what I say, virtual short effect and the RDS of the transistor. So overall we can see one thing here, we can see one thing. What we can see, whatever the resistor which was resistor or capacitor which was present here, it can be split into the two parts and it can be shorted to the virtual node, virtual ground node. Okay, so it can be shorted to the virtual ground node. So any resistor which was presented in between can be split into the two halves, and they can represent nothing but a R out of the transistors. So overall, we can analyze the circuit like, if this is the practical circuit where the RDS is there, we can find this whatever. This is the virtual short 0. So what I can say, V out 1. V out 1 is nothing but minus GM R naught 1 times V in 1. That is simple. So the register present in between, we can say a resistor or any impedance connecting both the outputs of differential structure can be splitted into two halves, and they can be treated as, so this was the thing I was trying to make here clear. So whatever the means impedance is available in between, whether it is a capacitor, inductor or resistor, any impedance in between, it can be splitted into two halves, and the midpoint can be shorted. Shorting means if midpoint is shorting, this node is also shorting. So actually from drain to source, these particular impedance can be connected. So in general, these impedance can be connected from source to, yeah, so these impedances can be connected from, so this is my some particular load, and there is some other load. The mean to say is that, so this mid impedance can be splitted, or I will say here is current. Okay, so this mid impedance can be splitted and treated as a RDS of both the input pairs. So it can be splitted and given as a RDS to both the structures. Okay, so this is the conclusion. What other thing that I can discuss about this circuit? I think these things are clear. I think also I asked about the zero, but there is no zero. We see zero in some other structure where there is any direct connection between input and output, then zero can be there. For any structure, so in this we can see this capacitor was here, so no input to output direct connection, or I can say at infinite it can happen like this. So suppose this is V in 1, this is V in 2. Okay, so we can see this is my output 1, this is my output 2. In general, there is no zero because there is no direct connection between input and output. If I am not considering here gate to drain capacitances, they are very small, then there is no direct path between input and output. But one thing that I can see here, one more analysis I want to show you. Okay, this in general I am shorting, but it is a current source, so I should mention here, otherwise you will be confused. So this is the current source. So the point that I want to make here is that in general there is a no direct connection between input and output. So I can say there is a no zero. But what to speak at very high frequency? At a very high frequency, my cap is shorted. And what will happen? What about the differential input? Differential input is still there. So V in 1 equal to Vi divided 2, V in 2 equal to minus Vi divided 2. So differential input is still there. This is called V in 1 minus V in 2 equal to Vi. Differential input is still there. And what about the outputs? Output 1, yeah, nothing but this capacitor is shorted. Output 2. So output 1 minus output 2 equal to 0. So overall I can say differential output equal to 0. Hence 0 is existing at infinite. The omega equal to infinite means infinite frequency. This is the frequency. So I told you before that it is a first order system. At infinite there is zero. So we can see this thing that this is a stable system, because the first order system is unconditionally stable. So you can see thing here. So if there is a means root locus, this is my that I call 1 upon omega p1, and this is my 0 at infinite, 0 at infinite. So closed loop poles are always tracing toward this infinite 0. So what we can see here, the system is always stable. The first order systems are unconditionally stable. So this is the root locus. Closed loop poles are on real axis and in negative half plane always. So it is unconditionally stable. First order systems are unconditionally stable. Little bit I am talking about this stability concept here. Okay, they are unconditionally stable. So this thing that I can say about the circuit. What more? Okay, yes. If I talk little bit about its closed loop function, then what we can see, we have seen anything. Okay, we have seen there's its open loop transfer function is a naught 1 plus means sy omega p1. If I draw its closed loop transfer function, suppose it is used in the negative feedback system and there is a beta factor, and what you can see, a y as 1 plus beta a of s. So from here we can see a naught y 1 plus sy omega p1. This is my a of s, 1 plus beta a naught 1 plus sy omega p1. It is not the part of this discussion, but I am just extra discussing here. A naught divided by 1 plus beta a naught plus sy omega p1. It can be written as a naught 1 plus beta a naught divided by 1 plus s omega p1 beta a naught. Okay, so it can be written as a naught dash divided by 1 plus sy omega p1 dash. So what are this a naught dash and omega p naught dash? So in negative feedback we can see this, my gain is changed from a naught to a naught dash, and my 3dB frequency is also changed from omega p1 to omega p1 dash. What is a naught dash? This is nothing but a naught divided by 1 plus a naught beta. So what we are seeing here, this gain is reduced by the factor of a naught beta, 1 plus a naught beta, and this bandwidth is increased, omega p1 times 1 plus a naught beta. So on the log scale we can see what we can see. And what about the UGB for the closed loop system? Omega UGB is still same, because it is nothing but a naught dash multiplied with omega p1 dash. So it is coming as still a naught into omega p1, which is nothing but omega UGB of open loop system. Okay, it is still same. This is a closed loop system, it is an open loop system. So from here what we can see about the plots, just I am putting the negative feedback here and beta factor. So what you can see here, what we are seeing here, omega on log scale, this is the gain on dB scale. So what was my open loop gain? It was something like that. Okay, so it was my a naught and this frequency was omega p. So what about the closed loop response? Closed loop response is this is something like that. Bandwidth increased, bandwidth reaching somewhere here, omega p1 dash, which is nothing but multiplied by the 1 plus a naught beta factor, and UGB is still same, omega mu, that is called a UGB, still same, and gain is here reduced to a naught dash, which is nothing but divided by a naught is divided by 1 plus a naught beta factor. So what we can see, the bandwidth is increased in the closed loop system. Bandwidth is increased, but cost is reduction in gain. So what extra that we can see, yeah. So now one thing that I will also analyze here about the stability. Yeah, of course, second order system is always means sorry, first order system is unconditionally stable. Still, I would like to compare both open loop and closed loop gains on their phases also. So for the first order, this is my omega p1. So somewhere here this gain will be for minus 45, and after that will be like minus 90, and somewhere here it is minus 45. So what about the phase of closed loop system? You can see here somewhere here it is nearly minus 40, and after that it is trying to reach minus minus 90. Okay, so at UGB, what you see, UGBs both are same, UGB of both are same. So what can we see, what can be seen from here? Okay, so what is the angle at the UGB? Angle at UGB for this is, let's say it is a okay, let's say this is exactly minus 90 degree, and it is somewhere around minus 80 degree, let's say, that's the example. So what we can see in general, what you say, phase margin is 180 plus angle of the system. So what is this, 180 degree minus 90, the phase margin of first order system is, open loop first order system in minus 90 degree, and for the closed loop system, PM for closed loop system is 180 minus 80 degree. So it is, so this analysis is not that important, because anyway whatever the open loop system or closed loop system, if it's a one pole system, it is unconditionally stable, so there is no point of discussing the phase margin here. This will be much important when we will discuss the second order system. So phase margin will be much important in the second order system discussion. Phase margin discussion much important in second order system, important in second order system. Okay, there we will see how this closed loop poles moves, and when the system can be stable, and what should be the UGB, what should be the phase margin for the proper stability, and what are the other things that can cause instability in second order system. We will see in some other CTQ or maybe in some other topic discussion. So I think these are the things that I can relate about this circuit. If something is more which is missing, you can post me in the comment or somewhere on the Telegram. We will see what more can be analyzed about the circuit, and later we will see the frequency response analysis of the 5 transistor OT. A lot of things we will see from there, and after that in the two-stage op amp part we will see rest of the things. So thank you.